We are now in the fourth step of the transportation planning model. First, we looked at trip generation, how many trips an individual makes on a given day as a function of their demographic characteristics, their socioeconomic attributes, their location in space, and so on, and how many trips would be attracted to destinations. We looked at destination choice, how many people would go from origin I to destination J as a function of trip purpose, as a function of the number of trips that were generated in I and attracted to zone J, and as a function of the impedance between I and J. The farther away places are in space or in terms of travel time, the less likely places are to interact. The impedance might come from the log sum of the mode choice model. The mode choice model predicts how many people going from zone I to zone J will use mode M. If mode M is driving and using the road network, we then want to know what routes people are going to take. The question about route choice is how travelers choose a route. We have a similar problem for transit, how travelers choose which transit route to take. It's more complicated than we can do in this lecture because transit is a scheduled service. It depends not only on the spatial arrangement of the network, but on the temporal arrangement of the network, thus not simply on how to get from A to B on a network, but also when the transit vehicle from A to B arrives. It's a much more complicated problem. So how do travelers choose a route between A and B? How do you decide which route to use? You might choose the shortest distance route, or the fastest, or shortest travel time route. The shortest travel time is a good starter hypothesis that's widely used. How do you know what the shortest route is? If you look at old paper maps, there are tables which list cities and destinations, and you can find the distance of the shortest path and an estimated travel time. For long distance trips that are uncongested, that's probably a pretty good estimate. However, for trips that are congested, like trips to campus at 8:30 in the morning, your travel time varies from day to day. Some days it's faster than others. So the distance between the two places on a fixed route doesn't change, but the travel time between two places is very dynamic. It's different at 4 in the morning than it is at 8, and it's different at 8 in the morning than it is at 8:15. You might say an online mapping service, but those are not perfectly accurate, and they can only tell you what they think the time is going to be, not what it actually is. You might drive it and see what the time is, but that will only tell you the route that you're taking. How do you know what the time is on the routes that you're not taking? Each link has a link performance function, sometimes called a volume delay or latency function, relating travel time or cost on that link and total flow on the link. This is analogous to an average cost curve used in economics. The minimum time at the left reflects the free flow speed and distance. The right side reflects congestion. In this case, the widely used BPR function is graphed, named for the Bureau of Public Roads, which is the predecessor organization of the Federal Highway Administration. As the traffic flow on a link increases, the travel time a driver faces on that link increases. Think about a train. How close together are cars on a train? Well, they touch. If traffic were perfectly predictable and autos didn't brake, they wouldn't need any space on the road between them. In technical terms, they would have a headway of zero as many cars as wanted to could pass a point at free flow speed, say 60 miles an hour, subject to their having physical length. They could operate like a train. And if cars were infinitesimally small, we wouldn't even have to worry about length, and then there could be an infinite number of cars going through the bottleneck. Now, of course, cars have actual physical length, and they have some physical speed that they're traveling at. If cars never had to brake, they could go as fast as they were physically capable of going. But we have physical constraints. If the car in front of you brakes, you have to brake, or you plow into it, which is a bad outcome. There's a trade-off here. How fast do you want to go versus how safe do you want to be? If you want to be really safe, you leave a very long distance, what we call a gap, between you and the car in front of you. If the car in front of you is very unpredictable, you're probably going to give them more space than if they're very predictable. If you can see ahead of them, you might give them less space because you can anticipate what they might do. When you were in driver's ed, what were you taught about the car following the car in front of you? Maybe you were taught distance, for instance, 4 car lengths. But how long is 4 car lengths? Well, it depends on how long a car is. A Smart for 2 is 2,500 millimeters. A Mercedes S-Class is over 5,000 millimeters. Traveling 4 lengths depends on which car. Further, it doesn't differentiate by speed of travel, so that's not terribly useful. I was taught the 2-second rule. Follow it 2 seconds from the front bumper of the car in front of you. Maybe you were taught a 3-second rule. That is safer in general, but leaves 50% more capacity unused and thus lowers throughput. If every car followed every other car at 2 seconds, we would get 1,800 vehicles per hour past a point because there are 3,600 seconds in an hour, and 3,600 divided by 2 is 1,800. If every car followed at 3 seconds, we would only get 1,200 cars past a point. In practice, some locations see as many as 2,300 vehicles per hour, with some consistency. So cars in congested situations, not necessarily slow heavy traffic, but still driving at or near the speed limit, we can get 2,300 cars per hour past a point, which means they're following at less than 2 seconds. If they're following at 1.5 seconds, it is 2,400 vehicles per hour past a point. 3 seconds is safer. With 3 seconds, you're more likely to safely brake if the car in front of you taps their brakes than at 2 seconds, and certainly better at 2 seconds than at 1.5 seconds or 1 second. The more cars there are, the more interference you experience, and it's because they might apply their brakes and you are constrained in your actions. On multi-lane roads, some of this friction comes from lane changing. The simplest case is a single one-lane road with a double yellow line or barrier so that you can't change lanes. When nobody is merging in or out, this is called a pipeline section because it's like a pipeline. In this case, capacity is primarily determined by how close cars are willing to follow each other. This is a stylized example. The capacity is 1,000 vehicles per lane per hour. So when we talk about capacity in this course, generally we're talking about the capacity per lane. And here we have an expression which relates the travel time to the ratio of flow and capacity. The higher the capacity utilization, the higher the number of vehicles per hour trying to use the facility compared to the capacity of the facility, the more congestion there is. Travel time increases at a power of 4 in this example, and there's a coefficient to scale this. The free flow travel time on the link, if there were zero traffic, would be 1 minute. Thus, if you had a flow to capacity ratio of 1, the total travel time would be 1.15 minutes. If you had a flow to capacity ratio more than 1, it would go up as shown. And you say, how does flow exceed capacity? Capacity is the number of vehicles that can discharge from the link. The flow is really the number of vehicles that are trying to use the link. So if the flow exceeds the capacity, what happens? Well, everybody goes slower because they are getting in line to use the constrained bottleneck. This accumulating line we call a queue. So imagine 1,000 people per hour tried to go through a revolving door and the door could only accommodate 600 people per hour. At the end of an hour, how many people would be left in line? 400. You'd have a queue 400 people long. It's the same idea. In this particular example, if the flow equaled the capacity, you could get all of them through in an hour. They'd slow down, and they're slowing down because of the interference. If you had a flow that was 2 times the capacity, then it would be 2 to the 4th, which is 16, times 0.15, or 2.4. And 2.4 plus 1 minute of free flow time gives you a travel time of 3.4 minutes. If you had a flow to capacity ratio of 2, the equation implies that the travel time would more than triple. The time that the driver faces is different than the travel time that the driver imposes on everybody else. We have what we call an average cost and a marginal cost. The average cost is the cost in terms of travel time that the driver sees. More formally, the average cost is the total cost divided by the total flow. In other words, how long it takes a driver to traverse a particular facility. So in the example before, when the flow to capacity ratio was 2, the average cost would have been 3.4 minutes. The marginal cost is the cost of delay that they're imposing on everybody else. So you can think of this as an incremental cost, the difference in total cost with and without the vehicle. That is the average cost with the additional car multiplied by the number of people experience that cost minus the average cost without them, multiplied by the number of people experiencing that cost. The marginal cost is the change in total cost over the change in flow, dc dq. This should cause you to recall your calculus. Queuing occurs when demand exceeds capacity. You use the link performance function to estimate this cost. On a link, the capacity is thought of as an outflow, demand is an inflow. If the inflow is greater than the outflow for a period of time, there is queuing and delay. For example, for a 1-hour period, if 2,100 cars arrive and 2,000 depart, 100 are still there. The link performance function tries to represent that phenomenon in a simple way.